So in this section, we're going to talk about standard solutions. A standard solution is a solution whose concentration is accurately known. Now, we could buy standard solutions from companies such as Flynn or NASCO or things like that. But really, for the most part, if you know a little bit of chemistry, you can pretty much make all of your standard solutions right in the lab. So for instance, if I was going to talk about HCl, hydrochloric acid, in my lab, in the back room, I have a big old bottle, about a liter, 2 liters I might be, of 12 molar HCl. From that, I can make all the other concentrations we've used this year. I can make 6 molar, I can make 3 molar, I can make 1 molar, I can make 0.1 molar. I can make any molarity from 12 on down just by simply diluting it. So, with knowing a little bit about standard solutions and a little bit of math in order to determine the concentration of things, we can make our own solutions and save the district and or your company a lot of money. So, let's talk a little bit about how we would go about doing this in a lab setting. So, here's an example. It says to analyze the alcohol content of a certain wine, a chemist needs 1 liter of an aqueous 0.2 molar potassium dichromate solution. How much solid potassium dichromate, at least I'm saying it's dichromate, I hope it is, must be weighed out to make this solution. So let's highlight some important information. We need 1 liter of a 0.2 molar solution. We want to know how much solid must be weighed out to make this solution. So this should indicate to us that we're looking for an amount in grams. So the first thing we're going to want to do is start with whatever given is not a conversion factor. So recall from our previous video that molarity is a conversion factor. It's in moles per liter. So we don't talk about molarity in terms of a given. We talk about it as a conversion factor. So the only given in this problem is the 1 liter of the solution. So we're going to start with 1 liter of the K2CR blah blah blah. By all means, feel free to abbreviate things like that because I know it gets a little bit tedious in order to write the K2CR2O7. Now, if we have 1 liter on top, on the bottom we also need to have 1 liter so that we can use this conversion factor. 1 liter is 0.200 moles of that K stuff, K2 blah blah blah. Now, I need to know how many grams is needed in order to make this solution. So, I know that 1 mole of that K2CR2O7 potassium, I believe it's potassium dichromate, weighs 294 grams. K2 blah blah blah, K2 blah blah blah. So, if I go ahead and I do all my math, that comes to 58.8 grams of K2CR2O7. So let's not stop here. Let's talk about how we would physically mix up this solution. So here's what I would do. In my back room, I have these lovely little things called volumetric flasks. They have very long necks. And the reason why they have a long neck is because they are made to accurately measure a volume of solution. So in the neck or on the neck, they have an etching for a certain volume. So in this case, we would want to find one that is for 1 liter. That means if I fill my water completely up to that point, I will have 1 liter of solution, no more, no less. So if I'm going to make this, what I'm going to do is go to my balance. I'm going to weigh out 58.8 grams of the potassium dichromate. I'm going to pour that in to my flask. Now keep in mind that a solid such as potassium dichromate actually takes up volume. So I wouldn't want to put 1 liter of water in and then add my potassium dichromate because, well, it could overflow. And if it doesn't, you certainly now have more than 1 liter of solution. So what you do is you put in the solid and then you add enough water to get up to that 1 liter line. So we'll then fill this with water. How do we fill things with water? We use our blue highlighter because, water's blue. I don't know. So then we fill it up to water to that 1 liter line, and then we would put it on a stir and stir it, or we would let it sit long enough for it to be able to stir. When we're done, then we can pull it into, or we could pour it into some kind of vesicle to hold it. All right, so that's how we would physically go about making that solution. Now, what if I have something like 12 molar HCl? What do I do with that? Well, 12 molar HCl is a well-known concentration of 100% concentrated hydrochloric acid. I can then use this equation that's here, M1V1 equals M2V2, in order to figure out how to dilute the solution. How does it work? Well, this is the molarity at time 1 times the volume while it's that molarity at time 1. This then would be the molarity at another time, we'll just call it time 2, times the volume of that same molarity at time 2. So it's a very simple equation. You can actually do dilutions using dimensional analysis, but this equation is much easier to remember. Let's see how it works. If we go down here, it says, or it asks, what volume of 16 molar sulfuric acid must be used to prepare 1.5 liters of a 0.1 molar H2SO4 solution? So let's highlight our important information. We have 16 molar sulfuric acid. We have 1.5 liters of a 0.1 molar H2SO4 solution. And so we have a lot of information, and you need to recognize that we're preparing a new concentration of something. So I'm going to say, all right, here's my M1V1 equals M2V2. I need to identify what my M1 and my V1 are, and then I need to identify what my M2 and my V2 are. So as I'm reading this, I'm saying, okay, my first state in my hands will be 16 molar sulfuric acid. That's a molarity. So that goes in the first state. Then it says that I'm going to make 1.5 liters of a 0.1 molar solution. So in my ending state, I'm going to have 1.5 liters of a 0.1 molar solution. So what is my unknown? Must be V1. Now you can fill in the X, or you can just use it as V1. But as I go ahead then and set up this problem, you'll see that I will have 16 times V2, or X, equals 0.1 times 1.5. And from there, it's simple algebra. Divide both sides by 16. And the volume of that 16 molar, oops, sorry, that should be V1, not V2. The volume of that 16 molar solution that we need in order to make 1.5 liters of the 0.1 molar is 0.009 liters. Now that doesn't seem like much, but let's remember our conversions. That's really the same as 9 milliliters, which is an amount that you can actually measure and is something feasible. Now, if I'm actually going to make this, acids follow a different rule, and I want you to keep this in mind. Acids have a very special rule. The rule is this: do what you add, add acid to water. All right, so here's the situation. Remember way back at the beginning of this unit, I had mentioned to you that water has some really amazing properties, and one of the properties it has is a great heat capacity. When hydrochloric acid hits water and it ionizes, it releases a great amount of heat. Water is able to dissipate that heat without causing any harm to the container or to anything else around it. But if I were to put water into the acid, acid cannot handle the amount of heat that would be produced. So, of course, you want to know, is it going to explode or blow up? The answer is no, it doesn't really explode. It does kind of blow up. There's no fire by any stretch of the imagination because there's no fuel to burn. But it does get very hot. It can steam. It can boil. It can then shoot that hot, steamy liquid out of the container and harm you in some way. It can also produce a steam that you would then breathe in and could harm your nasal passages. So why do they use oughter instead of ought to? Maybe you know this word instead, ought to. So in other words, do what you're supposed to do. Add acid to water. Don't add water to acid. So we use oughter because it rhymes. Get used to that. All right, so anyhow, how would we do this then? Well, let's say that I had another one of those wonderful volumetric flasks. Here's my wonderful volumetric flask. My drawings do not seem very great tonight, but we're going to go with it. We're going to say that this volumetric flask holds 1.5 liters, which is nice and convenient because, oh, look at that. We want 1.5 liters of the solution. So, unlike the previous problem, instead of just taking this 9 milliliters of acid and putting it in the bottom and adding water to it, we can't do that. So what you're going to want to do is add a certain amount of water. Let's just say this amount. How much doesn't really matter as long as it's plenty of water to allow for the solution, the standard solution to be added and for it to be diluted. You can add water to the mixture once the acid has been added. So now, I don't know why, let's just choose red as our acid. So here's our little bit of acid that we then have to put in. And then we would take our water and we would continue to fill it up so that the whole vial was full. That acid can then dissipate and dilute out and become a lesser solution, a lesser concentrated solution. So do keep this in mind. You're not going to be mixing a lot of acids in here, but it's always a good rule of thumb that if you're going to dilute anything, start with some water in it, add something to it, and then bring it up to volume. So that's how we would use dilution, M1V1 equals M2V2, and that's how we would use standard solutions in a lab.